Okay, so we're continuing with a bunch of free response questions, this time on rotational inertia. So our objectives are to determine the acceleration, speed, and horizontal displacement of a thin hollow hoop which rolls down an inclined plane and off a table. I've got a number of formulas over here quickly. Just go down a couple of these. Let's take a look at these two. So what are these two referring to? What do they mean?
Torque.
Okay, so torque equals, what's our R?
R is the distance from center of mass.
Okay, and that's our force. What about this I down here?
I is inertia.
So that's my moment of inertia.
Mm-hmm.
And it's kind of equivalent to a mass almost. So this moment of inertia times alpha. What is alpha?
Angular acceleration.
Angular acceleration, which is our angular equivalent to acceleration. Okay, cool. So starting us off, we've got a thin hoop of mass m, radius r, and rotational inertia mr squared, released from the top of the ramp of length L above. The ramp has an angle with respect to the horizontal tabletop, which is fixed, so that's here. The table is a height above h above the floor. I assume that the hoop rolls without slipping down the ramp and across the table. I want to express all algebraic answers in terms of given quantities and fundamental constants and derive an equation for the acceleration of the center of mass of the hoop as it rolls down the ramp. Where do I start?
So angular acceleration of the I think so wait there is no mg sine theta
Okay.
with with kinematics.
Okay, so then I've got the force that's pulling us down and then minus the force of friction, right? So you said our net force, MA, is equal to mg sine theta minus our force of friction.
Mm-hmm.
Okay, that's fine.
Is equal to ma.
Right. So that's my net force. Then I'm also going to look at the torque. So that's F cross R, in this case force of friction, times R, is equal to our moment of inertia times angular acceleration. And I'll need to start making some substitutions.
Yep.
Okay, so what's my moment of inertia?
So mr square.
Okay, so this is force of friction. Our radius is R. Capital R was given to us, so I'm going to substitute that in. Equals our moment of inertia here, capital M R squared, times angular acceleration. What's my angular acceleration?
A over r.
A over R. Okay, so we can substitute for that. That R is my radius, so I'm going to make that a capital R. Okay, so let's use this one, and we'll solve for force of friction, and then maybe we can substitute into the other one and figure out what's going on with our acceleration. So what happens if I solve this one for force of friction?
So mg sine theta minus ma.
Okay, I think you're a
Mr
step ahead of me.
squared.
Yeah.
Wait, yeah. Wait. So R cancels out. So it's ma.
Okay, the force of friction is just ma.
Yeah.
So that means my net force ma is equal to mg sine theta minus ma. Okay. And we
Yes.
were looking for an equation for our acceleration. Um, so all of my m's are going to cancel, and then I'll need to move that a to the other side. So that gives me 2a is equal to g sine theta. And move this
Divide
one to
by
the other
2.
side, divided by m, and then divided by 2 gives me g sine theta over 2 for our acceleration. Okay, they told us we have to express all algebraic answers in terms of the given quantities, that's m, r, and moment of inertia, and an angle theta, and fundamental constants. So gravity is a fundamental constant, so that's okay. Theta is one of the given quantities, so that's okay too. So I think we're fine.
Mm-hmm.
Any questions on part A?
Nope.
Moving on, part B. I want to derive an expression for the speed of the center of mass of the hoop when it reaches the bottom of the ramp.
Let's reuse energy.
Okay, if I'm going to use energy, how are you going to use it?
Mg L sine theta is equal to half mv square plus half I omega square.
Okay, I think that would work, but there's an easier way.
Mm.
Is there any way
Oh, kinematic?
we can use kinematics? Okay, so I'm going to use our second kinematics equation. Vf squared equals vi squared plus 280. Since we already know our
Mm-hmm.
acceleration, we'll be able to sub in for that. So I could say Vf squared equals 2AD, since we didn't start with any initial velocity, I don't think. Did we?
Nope.
No, we're released from rest. So our initial velocity was 0. Therefore, Vf squared equals 2. Our acceleration from last time was g sine theta over 2 times d. What's our d right now? I can sub for that too.
L.
L. Okay, then we can solve for Vf. So Vf is equal to root GL sine
G
theta.
sine theta R. Yeah, and the square root.
Yep. Okay, so we're good. Let's see, do I have enough space? I might. I'm going to try to do C here, just so we can see B as well. And if we don't have enough space, I'll throw over to the next slide. Derive an expression for the horizontal horizontal distance from the edge of the table to where the hoop lands on the floor. So we're going down here, and it's going to fall some horizontal distance away from the edge of the table, which I'm going to call distance, we'll say X. What do I need to do?
We also use kinematics.
Okay, so if I'm going to use kinematics, then how can I know when an object hits the ground?
That's when the formula is 0.
Formula for what?
Y equals to I don't know. I have no idea except for kinematics. But I think we have to use kinematics for sure.
What you were saying was right. So something has to equal 0. But what has to equal 0 when an object hits the ground?
Y
Y. What does Y
is
represent?
0. Um, V initial times t and half mv squared. No,
Okay,
half
okay, I
gt
see.
squared.
So Y is height, and you're giving me the formula right now. So 1/2 gt squared plus your vertical velocity, initial times time is what you said, plus our initial height. Would give us our height at any time. So that initial height would be h, right? But my height at this time when we hit the ground should be 0. Right?
Yep.
Okay, so if I do this, I'll have negative h equals, since this is 0, 1/2 gt squared. That g is negative because of our direction. So when I go to plug it in, that'll be positive. So I could say h is equal to 1/2 gt squared. And this is really my difference in my y values, right? So that difference is going to give me h. Okay, so I could say t squared is equal to root, sorry, not root yet, 2h over g, or t equals root 2h over g. Okay, so this is the time when the object will hit the ground. How can I use the time when the object hits the ground to figure out how far from the edge of the table that the object will land? So this is projectile motion.
So v times t is equal to x.
Okay. Specifically our
So
horizontal velocity times time. Okay, so our horizontal velocity will be equal to the velocity that we got in part B. So that was our final velocity as we
yeah.
came down the ramp, right? We'll all be horizontal once we leave the table. So that is root GL sine theta. Root GL sine theta times root 2h over g. That's actually inside the root. Root 2h over g. Okay. I'm multiplying these two square roots together. So that means I can throw everything under the same square root. Is there anything else that I can do to simplify?
G cancels out.
Our g will cancel. Okay, so that leaves me with what?
Square root 2HL sine theta.
Okay, root 2HL sine theta is equal to my displacement, horizontal displacement from the edge of the table when we hit the ground. Awesome. Any questions on what we did for B or C?
Nope.
Okay, then part D. Our hoop is now replaced with a disc that has the same mass and radius. How will the distance from the edge of the table to where the disc lands compare with the distance determined in part C from the loop? So it'll be less than, the same as, or greater than the distance.
Hoop is replaced by a disc. Then inertia will be changed.
Yes. Is our moment of inertia going to be less with the disc or more with the disc?
More.
Okay, so our inertia is actually going to be less with the disc than with the hoop. We'll have less inertia, more translational energy. So does that mean we'll have greater speed or less speed?
Greater.
Greater speed. Okay. So greater speed, we could say something like the moment of inertia of a disk is smaller than with a hoop, giving the disk more translational energy. And therefore more horizontal speed as it falls.
Mm-hmm.
Okay. Any questions on anything we did today?
Nope.
Okay, let me check our scoring guide really quick and we'll see how we did. This one, I believe. This is question 3. Okay, so first part. Using the second law, torque equals IA. Okay, we did that. Correct rotational inertia. Okay, we did not do that. Is there another approach? Using conservation of energy. Okay, that's... I don't think we did that either. We did this one. Okay. We didn't use parallel axis theorem. We didn't directly solve for torque, but we did have a correct relationship for rolling without slipping of A over R. We did use the second law, and we did substitute in to get our answer. Okay, so I feel like we would get 3 out of those 5 points. I think. So I didn't specify here that we would get to... Well... We kind of did. So when you add these up together, you would get to...
Yeah.
I'm gonna give us 3 out of 5 just to be safe, because I'm not really sure.
Mm-hmm.
Okay, then... for B... Okay, statement of... It's a solution for B as with previous approach, but with points allotted similarly. Okay, kinematic relationship, we've got that. Substitution, we've got that, and acceleration. Okay, cool. Then for part C, height, time, okay, we're good. Substitution and distance, okay, we've got all of that. Then checking greater than, okay, and then 2 points for justification. The speed should be greater because rotational inertia is less. Okay, cool. So we should have that too. So I'm going to give us 13 out of 15, just missing those 2 points from part A.
Mm-hmm.
Oops. All right,